don't tell us much. So let's organize our X bar values into a frequency table. We have used a class width of 0.38. Okay, so that's the choice they have made to fit everything in 9 classes. That's the lowest to the highest lengths, and then used frequency to find relative frequency. Remember, this was out of 100 samples. So if there is only one fish in this range, then 1 out of 100 is the relative frequency. There were 10 fish in this range, so 10 out of 100 is the relative frequency. So you know how to find frequency and relative frequency. A table has been made. Earlier it has been dictated a class width of 0.4. Okay, so initially, well, when you calculate, you expect you had 0.4 class width. However, the choice results in the 10th class being beyond the data. All right. So consequently, they reduce the width slightly. So they were initially hoping to have class width of 0.4. 0.4 was insufficient. There were not. It was going beyond this range. So that's why they decreased the class width. Okay, to make sure there was some sample in every class. Okay. Now, we know that the relative frequencies may be thought of as probabilities. So we effectively have a probability distribution. So here is a class limit. So that's an interval. And then you have a probability. So this is a probability distribution. From each set, you get a certain probability. Okay. Because X bar represents the mean length of a trout based on samples of 5 trout caught by each child, we estimate the probability of X bar falling into each class by using relative frequencies. So basically, relative frequency is the probability. Okay. Now here are the 9 classes drawn. Notice they are more or less symmetric. Okay. So estimates of probabilities of X bar values. Okay. And this is the relative frequency. The bars here represent our estimated probabilities of X bar values. The bell-shaped curve represents the theoretical probability distribution that would have obtained if the number of children were much larger. So in other words, instead of just studying 100 children, we could have gotten, say, 200 children, double the numbers. In which case, your rectangles would be thinner. You see, you have more classes, and the rectangles would be closer to your curve. Okay, so more and more rectangles, so thinner rectangles and more rectangles, you would have made them all fit under the curve. In other words, the curve would have been a much better approximation, would be more telling. Okay. Yeah. So if the number of children were much higher, the bell-shaped curve would represent the theoretical distribution that would have been obtained. Okay. Now that represents probability sampling distribution for the sample mean X bar of trout lengths based on random sample sizes of samples of size 5. So this was, we calculated, we drew this frequency table using size 5, samples of size 5. We see that the distribution is mound shaped and even and somewhat bell shaped. Okay, so this is mound shaped, even, bell shaped. Okay. Irregularities are due to the small number of samples used. We used only 100 samples and the rather small sample size. That is, for each child we had only 5. These irregularities would become less obvious and even disappear if the sample of children became much larger. If we used a larger number of classes and if the number of trout in each sample became larger, say, suppose each child had, I don't know, 20 fish and we took 500 children, then, well, you would have a better approximation to the curve. Okay, 500 children means 500 rectangles. I'm sorry, not 500 rectangles, you will have many more rectangles. All right, so you have many more classes, which will help you approximate the curve better. All right, so the curve would eventually become a perfect bell-shaped curve. We will discuss this property at some length in the next section, which introduces the central limit theorem. Okay, so this particular example, right now we have only looked at samples of 5 each, and we have built a frequency table. It approximates a curve. Now what do we do with all this information? We will see what to do with this information in our next section. Until then, bye.